Hi everyone, my name is Zhen Rong and I'm a third-year PhD student at UCLA, working with Professor Tony Nowatzki. Today I'm excited to share our work, Stream Floating, Enabling Proactive and Decentralized Cache Optimizations. As multi-core CPUs continue to scale up, the cache system and the on-chip network have become increasingly important bottlenecks. Consider a multi-core system with mesh topology, and a simple program summing up an array A. Conventionally, the interface between the requesting core and the remote cache is based on simple request and response messages. A consistent challenge is that the cache is oblivious to program behaviors such as the access pattern, reuse distance, etc. And over the last few decades, architects tackled these problems with microarchitecture-only innovations for prefetching, bypassing, replacement, and coherence. However, even for well-structured multi-threaded programs, such a reactive cache system is far from optimal. Over the 12 multi-threaded data processing workloads we studied, 72% of cache lines evicted from the private L2 cache have no reuse, which not only causes thrashing in the private cache, but also introduces up to 30% extra network traffic for request and coherence messages. The reactive approach is the status quo because ISAs are treated as sacred, and within a conventional ISA, memory is manipulated with individual load and store instructions, which contain no information about future behavior. On the other hand, such information is readily available in the program anyways, which means the interface actually creates an information gap between the core and the cache. An alternate approach that we explore here is to encode longer-term memory access patterns as first-class primitives in a von Neumann ISA. We call these patterns streams. For example, here this linear access to array A can be represented as a linear stream, which enables accurate prefetching in the hardware as the pattern is well-defined. However, streams not only just define a sequence of memory access, but also contain much higher-level information like the access pattern, reuse distance, etc. Such information is more accurate, as the compiler has access to the higher-level program structure, and the cache is trying to recover exactly the same information. If we can directly offload the stream pattern to the cache, we effectively bridge the information gap with the stream information. This enables a proactive cache system, which is driven by streams and proactively transfer data to the core. Specifically in this work, we explored the idea of extending the interface between the core and the cache system to expose streams to the cache. Instead of sending individual requests to specific cache lines, the core sends one request for the entire stream pattern with little reuse, and the cache can run ahead of the core to stream back data. We evaluated this idea with Gen 5 and it achieves 39% speed up over state-of-the-art hardware prefetchers, with 36% of network traffic reduction. In today's talk, I will first focus on the insight behind this work and the new opportunities from offloading streams to the cache system. Next, I will discuss the detail of our implementation of stream floating and the interaction with the coherence protocol and the consistency model. Finally comes the evaluation and the conclusion. In order to better understand the insight and the new opportunities, we first make a key observation. For well-defined access patterns with little reuse, conventional cache systems introduce overheads that cannot be ignored. Here we count the percentage of evicted private L2 cache lines without reuse, and the number of fleets injected into the network from caching them. On average, 72% of evicted cache lines are not reused, which contribute about 50% of the network fleets. This indicates some major overheads. For example, caching data without reuse wastes the cache capacity, and tracking coherence states for data without reuse incurs significant overheads in possible invalidation and write-back. On the other hand, we found that 63% of such lines are from well-defined access patterns, aka streams, indicating that streams are widely applicable to cover such memory access behavior. To see how streams can be used to address this problem, let's first compare the conventional cache system with stream floating in 3 common scenarios. The first case is the affine access pattern like A of I. In a traditional system, the core will issue multiple requests to the cache, one for each cache line. However, the cache does not know the simple and well-defined access pattern, and is driven by numerous request messages. On the other hand, we can offload the whole stream pattern with a stream request and let the cache proactively transfer the data to the core. This effectively allows the stream to run in remote L3 banks, and we refer to it as stream floating, which reduces the request traffic and lowers the latency. Another interesting case is for indirect access patterns like B of A of I. Since the address is centralized in the core, only the core can issue requests, making a long dependence chain to first get array A and then array B. Also, indirect access usually has low spatial locality within the cache line, and some network bandwidth and the cache capacity is wasted on caching the whole line. However, stream floating can be helpful as it enables decentralized address generation. Now the cache can issue indirect requests on behalf of the core. This also reduces the request traffic as well as the data traffic, as we only need to transfer the required subline data. Finally, in well-structured programs, the cores may request the same data, but the cache have no way of optimizing for this by combining identical requests, and suffer from redundant request and response traffic. But streams define longer-term behaviors with only a few parameters, and the simple pattern matching is sufficient to detect the same request pattern from different cores, enabling the cache to multicast the responses and further reduce the network traffic. Overall, streams enable proactive and decentralized cache optimizations with lower latency and less thrashing. Now we can see that the stream is an excellent candidate to extend the interface between the core and the cache. Let me discuss how this can be implemented in microarchitecture. Specifically, we try to answer the question about what to offload, how to offload, as well as when we should offload. The answer to the first question is natural. We want to offload streams. A stream is a decoupled sequence of values or addresses. By decoupled, we mean that the access pattern has no data dependence on the remaining program. Here is an example program that sums over indirect access A of B of I. There are 2 memory streams, the direct access to array B and the indirect access to array A. We explicitly embed streams in the ISA. First, streams are configured before entering the loop. Stream data is exposed to the rest of the program using a special stream load instruction. Finally, a special stream step instruction will advance the stream to point to the next value. The memory ordering is defined by the first usage of the stream value. In the baseline microarchitecture, streams are handled by a stream engine in the core. Since we want to offload streams to cache, we also add stream engines to the private L2 cache and the shared L3 cache. The core stream engine manages stream configuration and issues requests to prefetch data. It also makes and cancels floating decisions. The L2 stream engine buffers the stream data and matches it with requests from the core stream engine. Finally, the L3 stream engine generates stream addresses and issues requests to the L3 cache controller on behalf of the core. When it's profitable to offload a stream, the core stream engine sends a configure message to the L2 stream engine with the affine stream pattern A of I. The L2 stream engine allocates the stream buffer and then forwards the configuration to the L3 bank where the first element A of 0 is mapped to. With the stream pattern, now the L3 stream engine can proactively generate addresses for stream A and translate the address using the L2 TLB. The data will be streamed back and buffered at the L2 stream engine, later drained by requests from the core stream engine. Since we know the stream data has little reuse in the private cache, stream data is not tracked by the coherence protocol, which further reduces the control overhead. To limit the remote stream's progress and avoid overwhelming the L2 stream buffer, the L2 stream engine sends out credits to the L3 stream engine. Credits are sent out at coarse granularity, such as one messages for multiple credits to further reduce control overhead. Also, as the stream moves forward, eventually the next data is mapped to some other L3 bank. In such a case, the L3 stream engine automatically migrates the streams to the next bank and keeps streaming until no credits remain. It is useful to slightly increase the L3 interleaving granularity to avoid too frequent migrations. Finally, the core stream engine can terminate an offloaded stream with a stream end message. The L3 stream engine can also directly release streams with fixed length. This completes the basic workflow of offloading an Affine stream, and by doing so, we are able to get multiple stream data with minimal control traffic. Since stream patterns are accurate and decoupled from the core pipeline, this enables deep and accurate prefetching. We can also offload an indirect stream by associating its configuration with the direct stream. Now the L3 stream engine can send out an indirect request to the target L3 cache controller, which responds directly to the core. This essentially decentralizes the address generation, and we only transfer the required subline data, since the spatial locality within one cache line is usually low for indirect accesses. Finally, neighboring cores may be requesting the same piece of data. With streams, this can be easily detected by comparing their stream parameters, and the L3 stream engine can multicast the data to different cores. We call this optimization stream confluence, which enables coordinated memory access between cores and avoid duplicated data traffic. The last question is when we should offload a stream. As mentioned earlier, we should only offload streams with no reuse in the private cache or any aliasing. This is done by combining both static and dynamic information. The compiler can perform static analysis to see if there's any possible aliasing stored, which is problematic for stream floating, as remote stream loads may very likely cause read-after-write misspeciulation. Also, the access pattern itself can tell us the reuse distance. We also maintain a stream history table to track the dynamic information, like the miss rate in the private cache and if there is an alias store, etc. When the core stream engine encounters a new stream, it will not offload it, but it executes it in the core to collect some history information to determine if the stream is suitable for offloading. Only when the stream passes both static and dynamic check will it be offloaded. When things goes wrong, for example, an alias with a store, the core stream engine can early terminate a floating stream with using a stream end message. This summarizes the basic approach, but there are still some questions. One major question is how the offloaded stream interacts with the coherence protocol and the consistency model. Here I will discuss how to integrate stream floating with a weak consistency model, as well as how to support strong consistency. For weak consistency models, we limit streams in synchronization-free regions. Therefore, we don't have to worry about writes from different cores. Also, as mentioned before, stream data is not cached, but buffered by the L2 stream engine and drained by the core stream engine. We extended the massive coherence protocol with a new get uncached request. Here are the transitions when the data is not in the cache. It is similar to normal GET request, except that the request is generated by the L3 stream engine. Also notice that the private cache is still in an invalid state after receiving the data, as the data is not cached. We still need to detect aliasing from the same core, which is hard as floating streams are decoupled from the core and run in remote L3 banks. Due to time constraint, we leave the discussion in the paper. Strong consistency can also be supported by performing coarse grain tracking on per stream state, which we call stream grain coherence. We also leave this in the paper. For evaluation, we implement a compiler transformation for the stream ISA extension in LLVM to recognize streams and transform the program. we use Gen 5 version 20 for cycle-level execution-driven simulation. We targeted 12 data processing workloads from Rodinia and microkernels. They are parallelized using OpenMP with AVX512 enabled. As for configurations, we evaluate 8x8 mesh topology with 3-level cache hierarchy. The baseline core has no prefetchers or stream support. We evaluated 2 hardware prefetcher configurations, with the stride or bingo spatial prefetcher at the L1 cache and a stride prefetcher at the L2 cache. For streams, we also compare stream specialized processes, which only support streams at the core stream engine, and stream floating, which offload streams to the cache. This graph shows the overall performance of all configurations for a subset of programs. For in-order cores with issue weights 4, both hardware prefetchers and stream specialized processes yield about 2 times speed up over the baseline core. Stream floating gives another 50% of speed up on top of that, as it can achieve deep, accurate prefetching with less network traffic. This is similar to out-of-order cores with issue width 8, except that the speed up drops to 39%, as the baseline core can hide much more memory latency. To better understand the benefits of stream floating, this figure shows the breakdown of requests to the L3 cache, classified as normal and stream requests from the core, requests from offloaded Affine and Indirect streams, as well as multicast requests from stream Confluence. Overall, 68% of requests are generated by the L3 stream engine, showing that a significant portion of the memory access can be floated. Most of the requests are from Affine streams, and there are some indirect access offloaded in BFS and CFD. Also, the L3 stream engine successfully recognized the multicast opportunities, such as the input feature map in 3D convolution. Next, we look at the network traffic breakdown. We counted the number of traveled hops for control and data messages. We also counted the overhead of all the messages to manage offloaded streams, for example, the stream configuration and the termination messages. We can see that hardware prefetcher actually increases the network traffic by 33% due to aggressive prefetching. However, looking at the stream specialized processor, we can see that streams are accurate as it never increases the traffic. The next configuration only offloads Affine streams, and this reduces the overall traffic by 30%. Most of the reduction comes from the control traffic, as we offloaded the whole access pattern at once and bypass the coherence protocol. Some benchmarks also see reduction in data traffic, as not caching stream data improves the hit rate in the private cache. Also, it only introduces about 2% of traffic overhead to control the offloaded streams. Enabling indirect streams and stream confluence further reduces the traffic for certain benchmarks, yielding on average 36% of traffic reduction. Finally, we show the estimated relative energy versus speed up for all the configurations. For these data parallel workloads, with stream floating, an in-order core with issue width 4 can even outperform an out-of-order core with higher energy efficiency, as the stream floating can fundamentally reduce network traffic and enable decentralized prefetching. To summarize, we refer back to this slide. We explored the idea of embedding streams in the ISA and directly offload to the cache. This bridges the information gap between the core and the cache, enabling proactive and decentralized cache optimizations. More importantly, as the number of cores and banks and the distance between the core and the remote cache increases, it is time to rethink the interface between the core and the cache. This work is just the start to explore rich semantic information in the ISA and use it to improve the memory hierarchy. Thank you.